So this tutorial is on recent advances in scalable retrieval of personalized recommendations. Now, in a way, recommendation has been an existing work for a very long time. I think here we would like to bring your attention to the idea of scalable retrieval, because in this tutorial we're going to focus on not just recommendation, but also the process of how do we retrieve those recommendations in real time for users at the point of time when they come to the application. My name is Hadi, and this tutorial I'm doing it with Andrew. He goes by Andrew. All right, and we come from a group called Preferred.AI, which is a research group at Singapore Management University. Now, Preferred.AI, we are looking in terms of preference learning and recommendations. There are a couple of us here. There are a couple of other group members at the back as well. We try to do research on recommendations and issues related to it, and we make our code available at GitHub. The address is code.preferred.ai, and also some videos there. Now, the goal of the research group is actually to do end-to-end recommendation framework. This is just an overview of the things that we are looking at. But the thinking is that if we are going to make recommendations, something that can be plugged into many different applications, there should be support along the way, all the way from the way that we are going to collect the data, how do we learn the preferences from this data, how do we extract the signals, to the algorithmic frameworks, the ones that we are going to build it into libraries so that people from academia, from industry can actually make use of it, as well as the issues of retrieval. So in some sense, what we're going to talk about today, some of them are going to touch on the idea of retrieval itself, and some of them are going to touch on the idea of recommendations. So there are two parts to the tutorial. Now the first part essentially is introduction, it's an overview. We will establish the problem of recommendation retrieval itself. So we'll talk about how recommendation actually has two phases. There is the offline phase when you learn the preferences of the users, and then there's the online phase when you deliver these recommendations to the users when they come to the application. Now, because of these two phases, they have slightly different properties and requirements. Because in a way, when you're trying to learn the recommendations offline, the issue is less about time, more about accuracy. But at the point of time when the user comes to the site or to the application and you want to deliver this recommendation, then time becomes a much more critical requirement, because he or she is not going to wait for a long time until the recommendation is delivered. So we need to be able to get these things as soon as possible to the user, and at the same time we don't want to reduce inaccuracy. That requires it gives rise to some issues that some of which we will be discussing here. And part two are going to talk about the main directions in the literature that are looking into solving this problem. How do we enable fast retrieval for personalized recommendation, while at the same time we are not going to reduce a lot in terms of the accuracy. So there are going to be three parts to the part two as well. These are three main strategies for recommendation retrieval. One is what we call approximate maximum inner product search. Now these terms may not all make sense now. I think we're going to get to them later. And the other two are what we call indexable representations and discrete representations. Now to get a good sense of what these techniques are, we have also designed a set of hands-on sessions. The hands-on sessions, we would like to actually intersperse it a little bit. But I think what the outline of today, probably what we will do is that we're going to focus the hands-on session after the break, so that during the break time we can make use of that time to help you to get set up, in case some of you still have problems in getting set up. So the first part before the break, we are probably going to talk about most of the fundamentals, so that by the time we get to the hands-on, we can go through them much more easily. Now let's start with the part one. So the idea of the recommendation is that the retrieval essentially is similar to search problem. Now what do we actually mean? Now the whole point of a recommendation starts from the idea that we all need to make choices. Now if we all make the same choice, then we don't have much of a problem. The issue comes because each of us individually, given the same options, we may actually go ahead and make different choices. And that creates a lot of problem for the application, because then the application will have to anticipate what it is that you at the individual level may want. And there are so many of us. And while the number of users itself is a problem, the other side of the problem is the number of possible candidates of the items that we're going to recommend. Now, what do we mean by that? Now, for example, right, so let's say we're looking for men's shoes. Now, of course, in the old days, we would go to the store and we will be choosing among the things that they have at the store itself. Now, the store can carry some number of inventory, so most likely you'll be choosing between a few possibilities, and you already have some things in mind like the color, the size, but you're going to be choosing among a few possible options. But today we don't do that anymore, right? So we all go online and we buy almost anything online, and shoes probably being one of them. Now, at Amazon, supposing that we are looking for Amazon shoes, so this is an estimate, probably a year old. There are 133,000 possible results. So we can't possibly go through all of them. So we're gonna have to rely on the system to figure out which of these 100,000 options are going to be suitable for us. Now, that is a lot of things even for the system to go through, because in a way it has to estimate your preference for each one of them, and that takes a lot of time. Now, this is just at Amazon. Supposing that these are examples from different countries. This is the Amazon equivalent, kind of like that. This is in Indonesia. So this is the Indonesian term for shoes. There are now 1.7 million possible results. So the number of possibilities keep increasing. Now, this is Taobao. So I checked for the shoes. So they are estimated based on the number of pages that you have to go through to look at all of them. There are actually 4 million possible results. Now, the thinking here, of course, is that recommendation tries to identify a small subset for you to look at. But the problem that I'm trying to point out here is that even for the system to try to construct an individual personalized list, they have to go through millions of possibilities just in order to identify the top few that you might like. And they have to do it for every single user. Now, most of the time, they don't anticipate when you come. So you will just come to the site, you search for certain keywords, and the system has to respond immediately, and it has to estimate your preferences across this number of results within essentially milliseconds. Now, the solution, of course, is to do recommendations, but the important thing is not just the recommendation itself, which itself is an important problem, but we are going to look at the issue of retrieval. Now, before we talk about retrieval issues, right, so we're going to talk about what is the thinking behind this recommendation. We're going to look at some basic techniques. This may be some fundamental techniques. The reason why we want to go through a couple of basic ones is because we're going to build our talk on that. A lot of the techniques in terms of speeding up the retrieval are essentially based on the fundamentals of existing techniques like matrix factorization, right? Now, the idea of matrix factorization itself, it gets popularized because of this Netflix competition. So it was more than 10 years ago when Netflix, it was then essentially a DVD rental company. It has a rental business, and it had a lot of inventory. Everybody wanted to watch the same few movies because that was what was playing in the theaters. So their problem was that they had a lot of inventory of all these DVDs. Some of them may be old movies, and how do they actually increase the viewing time? They have to recommend it to different users. Now, the contest itself was based on a $1 million prize, and the requirement is just for you to beat the existing system by 10%. Now, the 10% was based on a recommendation metric that is frequently used, which is essentially what is called root mean squared error. And the idea is that supposing that there is an existing rating value, and you make a prediction for that rating, which we call it a function of FUI. So you take the error and square that error, and you take the average across all the ratings that you have in the test set, and then you take a root. Essentially, it represents a kind of average deviation from the ground truth. And the smaller the deviation, the better is the results. And the whole point about Netflix competition is just that you want to minimize the error. You want to beat the existing error by at least 10%. And the data set was huge for that point of time. So that was like 100 million ratings based on about 500,000 customers and about 17,000 movies that was released as part of the competition. Now, the competition itself was finally won by coalition, because even by the end or towards the end, individual groups were not exceeding the 10%. So they started to build coalitions that combine in ensembles some of the techniques that they were building together, so that they make up a better technique. And finally, at some point, 2009, one group beat the performance of the existing technique by 10%, and eventually they get the $1 million. Now, the point of why I bring up this idea of Netflix prize is that it spurred a lot of research into recommendations. There were workshops, there were conferences, there were things that people were doing to look at this problem. And one of the things that came out of that is the importance of factorization models. That was essentially the time when it gets popularized by a lot more, because people realize that factorization is actually quite effective. Matrix factorization is very effective at predicting the ratings that the teams were using, because a lot of them were publishing their works in workshops and conferences, and essentially it started the whole thing about how matrix factorization is fueling the recommendation technologies. Now, I would just give a little bit overview of matrix factorization. I think most of you are probably familiar, but just for the benefit of those who are not yet familiar with matrix factorization. Now, the idea of matrix factorization is to think about the users and the items as a matrix. So on one dimension, you have the users. On the other dimension, you have the items, and you have a matrix of ratings. Now, these ratings are, of course, the matrix is incomplete. Most of the time, in fact, most of the time, you don't know what the value is. So, and that's why you want to be able to predict the values within the elements of the matrix. So essentially, it becomes a recommendation. So suppose that I have a new user, Gus, and I would like to know what is Gus' rating on some particular item, then I need to predict what would be the cell element. Now, the key intuition of the matrix factorization is that there are some factors, some reason as to why a person likes a particular movie. This could be for different reasons for different people. It could be towards gender, for example, like whether something is geared towards females or males, or whether something is like serious in terms of a movie that makes you think, or escapist, like a movie that stops you from thinking, and essentially you just want to enjoy the things. Now, if let's say there are a lot of such factors, then in a way, for any given movie, you can place it within this space of factors, and that will give you a sense of the different properties of the movie. Now, if you do the same for the users, so essentially we are mapping users and items in the same space, then the nearby users and items are likely to be related or similar in some sense. The user essentially likes the kind of properties that the item has. Now, the idea behind matrix factorization is that these factors do not have to be pre-identified beforehand. You have the matrix. Let's try to learn what these factors are. Now, to the extent that they are interpretable or explainable, then that is better. But in the case of recommendations, at least in the past, the focus really is on accuracy. It is much more important to deliver the recommendations accurately and fast, and later on, probably then we make some effort to try to explain it. Now, the basic technique for matrix factorization is as follows. So I'm just going to use some simple notation, and we hope that we're going to keep them constant throughout the talks, but sometimes we may be taking a click from a paper, so sometimes the notation changes slightly. But most of the time, what we're going to do is to represent a user in terms of a vector x, call it xu, an item in terms of another vector y, we will call it yi. Now, supposing m is the number of users and n is the number of items, so we will have a rating matrix. So this is going to be a rectangular matrix, m by n, most of which are empty, but some of which are filled with some rating values. And from there, we will try to factorize it into two submatrices. Now, the dimension of the factors is what we call D. So this is usually a number of factors. We set it to some reasonable number. It could be 50, 100, 200, depending on how many items and users we are really trying to model. Now, for each user, we will have a row of length d. This is the representation of the user, like a vector in a d-dimensional space that represents the user. And for every item, we will have a column vector also of length d. Now, suppose that I know what the vectors are for a user u and an item I just need to take the inner product of the two. So with the xu vector for the users, yi, the vector for the items, take the inner product, and we are going to get the prediction for the preference. So here we call it preference u on I. Most of the time, this is represented in terms of some rating value. Different systems will have a different range. It could be 1 to 5, 1 to 10, sometimes binary. Now, the objective of learning matrix factorization is to minimize this objective function. And this essentially is an error minimization objective. So we have the actual ground truth rating, RUI, and we have the predicted rating, which is the inner product of the two vectors, XU and YI. And the difference is the error. And we take the square of the error, and we are going to minimize essentially the square of the error. The lower the error, the better is the prediction. And in order not to overfit the data, we will add a couple of regularization parameters to keep essentially the user vectors and the item vectors small, so that we will focus on the variation across the different items or across the different users instead of on the magnitude. Now, this is a very basic form of matrix factorization, but essentially it underlies probably more than half of the papers that we see on recommendations. Now, there are two in particular. Okay, so I just want to mention the learning thing a little bit. Okay, so most of the learning algorithms for matrix factorization is based on a technique that is called a stochastic gradient descent. Because essentially we have an objective function and we would like to minimize this objective. So the way to minimize the objective is ideally if you are trying to minimize it across all the users, all the items at the same time. But the problem in particular is not convex. So then we need some ways to actually do that still within the right amount of time. Now, one way to do that is called stochastic gradient descent, essentially the most popular technique for learning the user vectors and the item vectors. Essentially, the idea is that you're going to learn it at the level of individual ratings. So we learn it one rating at a time, and for each rating, we are going to look at the error between the rating and the prediction, and then we are going to move the user vectors x and the item vectors y in the opposite direction of the gradient, proportional to the error. So then over time, as we do iterate over all the ratings, or at least a sample of the ratings, we are going to change and modify the user vectors and the item vectors to get closer and closer to the ground truth predictions that we use as the training set. Now, just to emphasize here, the focus of the tutorial today is not on the optimization or in the learning. In fact, I think soon enough we're going to talk about the retrieval issues that comes from the other recommendation. I just want to mention this because in case some of you are interested in matrix factorization, this is probably one of the concepts or the topics that you're going to come across. Now, there is another concept here that we would like to introduce because it's going to be visited again and again within the tutorial, which is the difference between what we call explicit feedback and implicit. Now, the feedback there refers to the idea that the user is going to give us some information or feedback about the item. And this collection of feedback is what becomes the training data for us to train the recommended systems. Now, the way that the feedback is expressed will give us some sense of whether the feedback itself is clearly stated, which is what we call explicit or implicit. Now, explicit feedback, examples of them are things like ratings or thumbs up and thumbs down. The reason why we call it explicit is because at the point of time when the user assigns a rating, he is basically responding to the question of, do you like this item or not? And so you buy something from Amazon, after the purchase, it will allow you to assign a rating from 1 to 5 stars. Explicitly, you are stating that you like the item, then you're going to give it a 5 star, or you really hate it, then you're going to give it a 1 star, or somewhere in between. Now, at that point of time, that expression is clearly about your preference. Now, in some cases, you're not actually being asked. So you're not being asked about what you prefer, but the way that you behave on a particular application, the way that you behave on a particular site may imply a certain level of preference. So for example, you may be just browsing different products at Amazon. So you're browsing different products on Amazon, you may be clicking on some things, you may be skipping some other things, and in that way, you might be expressing the thinking that you like the things that you click, and you don't really like the things that you don't click. Or maybe in terms of viewing time, if you spend a lot of time with a product, you read a lot of the reviews, then at some point you realize that that may actually be the product that you want. Now, this explicit and implicit feedback, okay, there are a lot of notations here, but I'm just going to point out some key concepts here. Now, one of the key papers on this is something called probabilistic matrix factorization, or we call it PMF. Essentially, it's very similar to the matrix factorization that we discussed earlier, but it is given in terms of probabilistic formulation. Now, if we look at the objective function, essentially it's going to come down to rating estimation based on the inner product. So this is the RUI earlier. They just use a different notation of IJ. And in this case, we have the user vector, the item vector, and the difference is going to give us the error that we are trying to minimize. The rest essentially are regularization. Now, the different case for implicit feedback, a lot of the work are based on this paper called BPR, Bayesian Personalized Ranking. And the key idea is the following, that it's implicit feedback because you probably observe some positive. So the user click on something, the user spends a lot of time with one particular product. Then you have the pluses. The pluses are, this is user item matrix, so you have the pluses. But for those things that the user has never seen, we don't have any information about whether or not the user is going to like it. For those, these are essentially question marks. Now, we can't really say that just because the user has never clicked on the item, that the user doesn't like it. He just may not be aware of it. So now the kind of preference signal that we get essentially is a weaker one, because what we can say at least is that it is likely that if he has clicked on an item, he will like that item better than something else that he has not clicked. Now, this is not true in all cases at all times, but it's true enough number of times that it carries a signal to the prediction or the recommendation. Now, the key difference in terms of that is that we are going to reduce or transform the original matrix 2D into a triple, a set of triples, like a user and a pair of items, and the preference that I express in terms of which item they prefer over the other item. So for example, given a user 1, if the user 1 has liked item 2, but we don't know what's going on with item 1, we are still going to infer that user 1 likes item 2 better than item 1. And what we are using to learn is the relative comparison in the preferences. So this is expressed in terms of a set of triplets, which we call Uij. Means user U prefers item I to item J. Now, the way that we are going to optimize this is to look at the difference between the preference functions. So earlier on, we are going to build a prediction for the user and item. So given that it's now a triple, like U, I, and J, one user, two items, we're going to say that the value for Ui should be higher than the value for Uj. And the Ui value here is the inner product of the user and item vector. And the Uj here is the inner product of the user U and item vector J. And we are going to minimize, we are going to make sure that they are going to be as different as possible. So basically two key ideas. The explicit feedback is based on the rating. The implicit is based on relative comparisons of preferences. Now, we come to the issue of the retrieval. So now this is the part where we observe that some issues start to appear. Now, the retrieval time, we have already learned the item vectors and the user vectors. The problem now is transformed into a slightly different one. In this case, the query is a given user. So a user comes to the application. We want to deliver a set of recommendations. Let's call that top K, right? So let's assume that you go to a particular application, you go to a site, we want to see a list of K. K can be any number. It could be 10 and so on. Now, given a user U, for which we already know the item, the user vector for that user U, we have to multiply that into this matrix of item vectors. And in this case, we have to take the inner product between XU and every single item. And as a result, we are going to get a set of predictions for all the items. Now, the prediction across all the n items will then have to be sorted for us to identify the top K. Now, in theory, it sounds very simple, right? So just make sure that for a given user, you multiply it into every single item, and then you sort that predictions in order to identify the top K. And that problem is something that is known in the literature as maximum inner product search. And the idea is that given a vector XU, find me the vector yi that has the maximum inner product when we multiply it with XU. Now, the top K of those will be the recommendation. Now, the existing approach, or at least what we see as most of the time what is being presented in the papers and so on, is essentially a brute force approach that is called linear scanning. Linear scanning means that we're going to try every possible item. So if there are n items, we're going to multiply XU with n items. If there are a million of them, we're going to do it a million times. And the cost associated with this will be the cost of computing the preference score and the cost of ranking them. Now, each one of them is going to have a factor of n, and essentially the larger is the n, which is the number of items, the slower it's going to take. Now, if time is not an issue, then it's not a problem. But for retrieval, time is an issue because you want to return the results essentially in milliseconds. Now, if you look at the number of products that any one website will have to go through to do this, they are not just in terms of 1 or 2 million. In fact, most of the time they're in terms of hundreds of million. I'm not sure whether it's going to be visible from the back, but this is an estimation in 2015. How many products does Amazon has? It's about 500 million. That is Amazon US. Now, if you look at Taobao, I tried to get this information. Most of the time, they try not to reveal this information because I suspect it's commercially sensitive information. But this is another estimation. Even in 2012, for Taobao, which is a Chinese website, there are already 700 million items on the shelf. Meaning that if you really have to go through 700 million items in real time, this is probably going to be pretty slow. So reducing the cost is important, and that's essentially what we will try to do. Now, to reduce the cost, we take some examples, some lessons from, let's say, databases. The idea is that for retrieval, it's useful to index. Index essentially is a kind of data structure, a different representation of your data that is optimized for retrieval. Usually it's oriented around having a query, and the query is going to go into the index and retrieve a small number of items, and this number of items are likely to be relevant to what you want, and so then we only need to rank those items. To the extent that we can reduce the set of items to a smaller subset, it's going to save us a lot of time. Now, there are 3 common indexing schemes for retrieval. I'm going to introduce each one of them quickly after this, but these are all relevant for the purpose of recommendation retrieval. And in fact, these are going to be the kind of index schemes that are most common in terms of this problem. So the 3 are locality sensitive hashing, spatial indexing, and inverted index. Now, each of them has been used in many different scenarios. In the case of recommendation, it turns out that there are some issues that are going to affect the quality of the recommendation when you use these indexing schemes. Okay, so now we are going to look at each one of them and see what is the problem. Now, let's start from the idea of locality sensitive hashing. Now, hashing is essentially a one-way function. So you have a piece of information, it's a string, a message, a vector, and you want to transform it to a lower dimensional representation. You can go from the original data into the hash code, but you can't really go the other way around. That's essentially the key idea behind hashing. Now, the point about hashing is to reduce dimensionality of the vectors, because originally the vectors that we have, the dimensionality could be in the hundreds, 400, 500. Now, if you can map it to a much lower dimension, suppose let's say into 8 bits, 16 bits codes, then first of all, it's a reduced dimension, so you can do this in a product computation much faster. On the other hand, you can also use different kind of retrieval techniques, like hash tables. Now, let's assume for now that we are talking about binary hash codes. So which means that we're going to have a set of functions, and each function is going to transform a value into one bit, whether it's a 1 or a 0. If you have B functions, you're going to have a code of length B. Now, depending on application, you want different kinds of hashing functions. Now, I think for cryptography, for example, what you want to make sure that your messages cannot be retrieved. So different messages should have different hash codes, and in fact, it's important that similar messages should have different hash codes, because then people cannot know that they're even similar. But for the purpose of recommendation retrieval, which is essentially a form of nearest neighbor search, we want two items that are similar to have similar hash codes. Essentially, we are going to use this as a form of dimensional reduction. Now, this kind of hashing is known as locality sensitive hashing. Now, this is for binary codes. Let's assume that the black dots are your data points, and they are distributed in the space in a certain way. Now, let's say you introduce one particular hash function, which is a plane, a hyperplane, that is going to divide your space into two. Now, anything less is going to be a 0, anything higher is going to be 1. Now, ideally, for locality sensitive hashing, it understands the notion of locality. So if two items are neighbors, meaning they are similar, then they should be placed within the same space, the same half of the space. So they will have the same bit code. So if they are different, if they are not neighbors, then you want them to have different bit codes. Now, if there are some guarantees in terms of the hashing function that ensure that this happens at some probability, then we call it a locality sensitive hashing. Now, if you have that, then what you do is that you take the data vectors, which are your items, you hash them. And when you hash them, you get binary codes. And these binary codes will allow you to construct a hash table. Now, items that fall under the same cell in the hash table, meaning they have the same hash code, they will be similar in terms of the original vector space, which is the original recommendation vector that we had at the beginning. Which means that given a new user, then we just have to hash that user so that it will go into the same hash table, identify those items in the hash cell, then we just need to estimate similarity with those items in the cell. So what it means is that we have now narrowed down a lot of the search space into just a few that will go into the same cell as the user. And locality sensitive hashing is going to give us some guarantee that those in the cell are going to be similar with some level of probability. Now, we're going to go to the problem of LSH for recommendation retrieval. Now, this is basically just a definition of locality sensitive hashing. It's expressed formally, but essentially the underlying intuition are below. So if you have two vectors, x and y, if they are similar, then you want the probability that they have the same hash bit to be high. If they are different, then you want the probability that they have the same hash bit to be, okay, there's a typo there, it's supposed to be low. Right, so high if they are similar, low if they are different. Now, they are different families. We call it family because what happens is that there is a distribution that you can derive hash functions from, and these distributions are guaranteed to give you the probabilities, like the probability thresholds, like how similar will they be, how different will they be. Now, there are different hash functions for different kind of distances, depending on what kind of distance you want to preserve. So one type of distance is what we call the L2 distance, which is essentially the Euclidean distance. This family is given by the following function. So in this case, you have a b, which is a scalar value. You have the r, which is a fixed real number. And then you draw different a vectors. And this is drawn from a normal distribution. And as you draw this one at a time, each time you're going to get a one hash function, which will give you 1 bit. If you need 8 bits, then you draw it 8 times, you're going to get 8 hash functions, which are going to give you 8-bit code. Now, this function is going to guarantee that the collision probability is expressed in this form. So in this case, there is at least some guarantee of what kind of probability you're going to get that they will have the same hash code. Now, a different one is for cosine distance, which is what we call the sine random projection. It's actually the same. Similarly, you draw the A vectors from a normal distribution, and then you multiply it into your original data vector x, and you just take the sign, whether it's minus or plus. And that will give you whether it's positive or negative, which is a binary. And again, this is going to be the collision probability. Now, LSH is useful. In fact, it's been used in many different kind of retrieval applications. But I would like to draw your attention again to the idea that this is essentially for L2 distance and for cosine distance. Now, what we want for recommendation is inner product. And inner product is not Euclidean. Inner product is not cosine similarity. And in this paper, in NIPS 2014, the authors proved that there cannot exist any LSH family for inner product search. Meaning that if what you want is to find inner product for retrieval, you can't use LSH as it is. It's just not possible. In a sense, it will not be able to give you any probabilistic guarantee as it is. Of course, the author is actually proposed a different way to do that. Now, that is a problem with locality sensitive hashing, and then I'm going to quickly go through another two. Essentially to give you a sense of why these index schemes are not working before we get to what are the possible solutions. Now, a different kind of index is called a spatial index or spatial space partitioning. So if you look at your latent vectors of the recommendation, so they are in a high dimensional space, let's call it, let's say, 100th dimension. What you want to do is to be able to split your space into different regions, so that given a new item, a query item, you can quickly identify where in this hyperspace will it fall into. Now, one of the ways to do this is what we call the spatial index. Now, let's imagine this is a simple two-dimensional space, and you have the red and the blues. You want to partition the space into two, so that once you partition it, you can identify two subregions, and these subregions are going to split the data, essentially, hopefully almost evenly, so that you minimize the amount of time that you will need to look at things. Now, the idea of spatial tree retrieval essentially is once you've got a tree, so let's say you have this space, and you're going to define recursive partitioning. Every partition is going to split the space into two, so essentially you're going to end up with a binary search tree in high dimensions. Now, this binary search tree will allow you to so given a new item, given the partitioning rules, you decide whether to go to the left or to the right. And essentially, on the average case, with log time, you can actually go down to the depth of this tree. And once you identify the lowest leaf node, then you can just focus on your search for similar items only within that sub. And if we do this partitioning well, we are going to be able to identify these similar items accurately. Now, there are different kinds of spatial trees, but they're all essentially a form of binary search tree. Now, the difference usually defined in terms of how you partition space. I'm just going to quickly go through a few. Now, this is a generic algorithm to construct a partitioning tree. And the intuition is very simple. The idea here is that we're going to define a depth, and this is the depth to which the recursion is going to go to construct the tree. So in this case, every time we go inside this function, what we're going to do is to find a split direction. When given a space, you find a way to split the space into two, so there can be many possible directions. We just want to find one direction based on some function. Once we find the direction, then we just need to shift it until we find the right point, which is called median, that divides the space into two that will have roughly similar number of items. Now, this is important just to make sure that your binary search tree is going to be relatively balanced to the left and to the right. Now, once you find a median, essentially you have now split the space into two. Now we are going to recursively do that for each of the left branch and the right branch. And after a few rounds, up to a depth of d, then we're going to get the tree that looks like this. Now, the classical thing is something called a KD tree. And the basic idea of KD tree is that we're going to cycle through the possible dimensions. So for example, in this case, there are 2 dimensions. So we are going to take each one in turn, and each time is going to be parallel to one of the dimensions. That means it's either horizontal or vertical. And if you have 3 dimensions, we're going to cycle through it. So dimension 1, dimension 2, dimension 3. Then you cycle dimension 1 again, and 2 and 3. And that way, you're going to construct the binary search tree. Now, this is not optimal, because simple but not optimal, because if you cycle through 1 to 3, in the way that you're cycling through is a robotic mechanical way, it may not actually optimize the way that your data is partitioned. So one way to improve it, which is what we call the maximum variance KD tree, is that instead of cycling, each time if you have 1, 2, 3, let's pick the one that is going to allow us to partition the data that will have the greatest variance, in sense. They will try to maximally separate the data. Now, but this is still not optimal, because it's still talk about cycling through the axis, meaning that each time the rule is only based on one axis, which is either horizontal or vertical. Now, if you allow a much more flexible axis, then you can do a much better way to split them. Now, this is called PCA tree, which essentially extends the idea of PCA. So you find the direction of maximum variance, and then you cut the space in that across that direction, so that you find a way to split them in the greatest into 2. Now, these are things in the PCA trees, but the basic problem with all these KD tree, PCA tree, and so on is that they are based on Euclidean distance. They are mostly used to solve like location, geographical problems. So in that case, Euclidean distance is important. Now, but we are looking at inner product search, and it turns out that inner product search is not equivalent to nearest neighbor search. So what is your nearest neighbor, and what is the one that gives you the highest inner product? They are different things. They are not the same thing. This is just a simple example. I mean, it's a synthetic example that we created just to show that if you have a user U and 2 items I and J, you can have the case when the inner product, that means the prediction in terms of the preference, for I is higher than J, whereas J is actually closer to U than I is. Meaning that if you use this index, a spatial tree index, for your retrieval, essentially you are not retrieving the ones that the user is most likely going to like. And that becomes an incompatibility that will cause problems. Now, the last one, just quickly, is the notion of inverted index. Inverted index is mostly used for document search. So I think this is probably an example of inverted index that we took it from a textbook on IR. Now, let's say you have 2 documents. Document has words. So now you're going to invert the form such that you have the words that are referencing the documents. So in that case, if you have a new query, which are the words, it will quickly tell you which documents are going to contain it. Meaning that in this case, you just need to confine your search to the subset that contains the query terms. So that allows you to narrow down the search space significantly. Now, ideally, we would like to use something like this, because you can narrow down the search space significantly, right? But recommendation vectors, they are not discrete. They are like continuous vectors. So it's not clear what would be the words, right? So words are discrete. You can immediately have a word and have it reversely referencing the document. So because of the continuous function of the real valued continuous functions of the vectors, that becomes a problem. We can't use it as it is. The second problem is the idea that it's based on cosine similarity. So most of the indexing for documents takes the vectors and then take the cosine similarity, which is the angle. So the smaller the angle, the higher the cosine similarity. And the problem here again is that the maximum inner product search that we want is not compatible with the cosine similarity search. Now we just look at the equation here. They look very similar, except for the fact that there are magnitude components here, and which means that the magnitudes do not participate in the cosine similarity, but the magnitudes do participate in the inner product search. And because of that, then the variance in the magnitude will cause problems for the maximum inner product search. Now, so the point that we are trying to make so far is this idea that the whole recommendation retrieval is based on inner products, and you want to retrieve it fast. You have to use indexes, but the existing indexes, whether it's a locality sensitive hashing, whether it's based on the spatial partitioning, whether it's based on the inverted index, out of the box, they will not be compatible. So because they are not compatible out of the box, then we have to do something about them in order to make it work with recommendation. Now, that's essentially the summary. Now, these are going to be 3 strategies that we're going to explore. Now, remember what we said earlier? We said they don't work out of the box, but which means that there is something we can do to them to make it work. Now, one way is that we still think of the problem essentially as 2 phases. One phase is to learn the preference vectors from some recommendation technique. It could be matrix factorization, probabilistic matrix factorization, BPR, and so on. And then we solve the retrieval problem separately. So in this case, what we're going to do is to take those vectors, and then we're going to do some kind of transformation that enables us to still do searches fast and accurately. And this is going to be part 1 that we're going to go into shortly. Now, there is a different kind of strategy, which is the thinking behind it is that instead of trying to do post-learning transformation, why don't we make sure that at the point of time when we are learning it, we make sure that the vectors that we get will be natively indexable. That means that this issue of the incompatibility with the indexing schemes will disappear if we take the pains to design recommendation techniques that will, in the first place, output latent vectors for users and items that will be natively indexable. Natively means that there's nothing you need to do to it. You just need to learn the vectors and then put it into the indexing schemes, and then they will just work like that. Now, there is a third strategy, which is called discrete representation. In this case, is to change the paradigm of matrix factorization in the first place. Because matrix factorization has always been defined in terms of real valued vectors. So in the discrete representation, they change representation to binary codes. And that essentially becomes a different way to represent user and item vectors. But the advantage of binary codes is that you can use hash tables natively. So in the subsequent parts of the tutorial, we're going to go through these 3 stages, these 3 strategies, and we're going to look at the different aspects of them and what are what has been done in the literature, as well as give you some examples of some of the hands-on sessions.